Let's start the chapter 5. This basically to most of you should be a review of the topics from statics. In these chapters, we're going to see the topic how to draw the shear and bending moment diagrams. The outlines here, I will first review the principle of drawing those diagrams, and then the second one give some examples. And then probably the third topic, the relation between the loading and the moment. Okay, then that could be the new to depends on how much you have explored from statics. And then finally we will apply to design of the beam, which means based upon what we've learned from chapter 4 and to the topics here we learned in chapter 5 here. Okay, so let's first see the principle of drawing the shear and bending moment diagrams. And so here is the notes. You probably have learned how to draw the shear and bending moment diagram from statics. Okay, if so, take this section as a review. If not, and learn it from here. Okay, and here we're going to draw the shear and bending moment diagram. The one important thing is about sign convention. The sign convention for the shear force and bending. So here sign convention is important things. Here you need to adopt. Here you need to learn here well. The people have the different sign conventions, but here in particular for this textbook and for the textbook we use here, I'm going to stick with the one I'm going to talk about shortly. And the motivations of the drawing the shear and bending moment diagram basically deriving from here. We have, in terms of the beam, we have so many kinds of the support: simply supported, and overhanging a little bit, cantilevered, and the over constrained, over supported, the simply supported, and this is over supported by adding additional here, and this is the double clamp. Okay, and either of these case is very common to see, and most of the time those beams are designed and in a way to support loading. The loading can be point loading. Point loading is like this, and can be distributed loading. Okay, this is the distributed loading omega, and that distribution of the loading is omega the Newton per meter, something like this one. And even though the distributed loading can be nonlinear, can be the function, say the straight line, or even more complicated, the nonlinear term here. Okay, similar to this case, and then the loading can be any of those things. Under these situations, we simply want to see if we have the loading like the say combined point loading and distributed loading, the goal is to know what is the distribution of the reactions throughout the beam. Okay, the purpose of the one is we want to know at any cross section. For example, in this cross section, and let me expose the free body diagram. This is the section I pick, and this is the support A here. I simply want to know what is the shear force and bending moment. Okay, the two are the reactions, and you should be able to obtain from taking the equilibrium equations and to obtain the two quantities. We simply, in these chapters, we simply want to know what is m, what is v, in terms of the functions x here. Okay, so we simply want to know what is the m of x and what is the v of x, and in the way we want to draw v as a function of x and m is a function of x. Okay, so basically that is our goal here. And the reason why we want to determine the distribution of the bending and shearing, and in particular for bending, we can see is this. From the previous chapters, we have learned the maximum. The M means the maximum, okay? So the maximum stress basically is equal to this number, the magnitude of the moment divided by the sectional modulus. It's called a section modulus, okay? So for designing of the beam, and that is the equation, the sectional modulus, as you probably have learned well, this is the geometric information. As long as we are given the shape of the cross section, this one should be readily available. The magnitude, basically at the bending, if we want to look for the maximum stress, and this bending should be the maximum somewhere in throughout the whole cross section. So that is the purpose why we want to know the distribution of the moment as a function of x. Okay, so that x measured from here. So we want to find out the maximum of the bending in the way that one we can introduce here to find this number. So that is one example to support our learning objective of drawing the bending diagram. And as far as drawing the shear diagram, and here we simply get ourselves ready for the next chapters. The next chapter will be dedicated to the transverse loading, and in which the shear information will be important. Okay, so basically here the goal is this. We are given, so here let me change back to here and align the things a little bit here. Okay, so since it's not aligned, so let me multiply this one quickly, so to see where I want to get it. I want to get aligned. You will see my action here. Okay, so here I get this one out, and then I get this out, and I want them to align well. Okay, so here you can see, okay, that's good. So basically here you can see I align the A to here, and I align the B and to this one, and C to here, and D to here. Okay, so here we take our measurement. So here is my measurement X. Let me change the color here. So basically X is measured from here, and 0 is here. So that is where the placement of the X coordinate here. And here we want to come up with two diagrams. This is the shear diagram, and this one is the bending bending diagram. Okay, and M of X. So in these chapters we are given the sound beams like this one, and this being the very original statement of the beam is like this. So here we have support, and sorry, not there. So here we are given loading applied to here and here, that is 20 kilonewton, 40 kilonewtons, and here we have support, here we have support here. Okay, so apply loading at A and C, and we have support at B and D here. So this is the original the problems, and then here we, based upon this one, we want to learn how to plot this diagram. So that is the requirement here. Okay, and how to do it, and that is the purpose we can try, and the purpose of the learning the detailed techniques here. And before doing this one, and I can give you the basic principle, and later on in the follow-up sections we're going to exercise the principle. The principle basically is this: we are given a beam, and under the certain the given loadings, that could be combined point loadings, and as well as certain type of the distributed loading here. Okay, then the drawing the diagram is this. The first one, we simply pick sections arbitrary, and that section has the coordinate x. We simply measure from A to here. That is the measurement. Okay. So once we have the sections, then we simply pick the cross section, and here you have two options to pick the free body diagram. And one is you pick these portions of the free body diagram, and let me draw that portion here. So you have this free body diagram, and to expose the section you choose. And the other options for you to choose is this free body diagram. This portion will also allow you to expose the sections you choose. So here you have these options, either options, and really up to your preference. And for these reasons, and we can see here, so that is the first option. If you choose this free body diagram, then in that free body diagram you have such loading, and this is reaction here. Okay, so that reaction included, and that is the one here. And then once you have this free body diagram to be chosen, then you should be able to determine V, and V is obtained by taking the force equilibrium in the vertical direction equal to 0. Then you should be able to determine the value of the V. And the reaction M, you can take the moment, for example, about point A equal to 0 here, then you should be able to determine the magnitude of the moment. Okay. On the other side, if you choose these options, and then as a free body diagram to find out the reaction here, and again, so in this free body diagram, this is the reactions happening at the support here is included in the free body diagram. So again, in terms of this free body diagram, you take the equilibrium equations, and you can also obtain the V prime and M prime here. And the relation between those things, because they are simply state the same, the cross section. So basically to them themselves, the V and V prime basically is the action reaction, which means their direction is opposite but with the same magnitude. Okay, so that is the reason here you are allowed to pick any cross section, either this piece or this piece, to expose, to try to explore what is the reaction here. And so again, similarly to the bending, they are simply action reactions, and they have the same magnitudes but the opposite direction here. Okay, so again, the principle is this. Here is a two kind of the conclusions. The first one is you pick the cross sections and arbitrary location, then you decide which portion of the free body diagram you want to pick, and to expose the sections you want to find out the reaction there, and apply the equilibrium equations to find out the value of the V and M. And right now you have calculated the magnitude of V and magnitude of M, and that is the value at this position X. Then remaining to build up the curve. Okay, so let me say this is a V curve. So 0, this is a V, and this is X. So now, for example, here you have calculated V here. So say V is this value, you calculate it. For example, say V equal to V0, you calculate the V0 here. Then right now you simply keep changing the selection of the cross section. You simply sweep your selections throughout the whole cross section. Basically, you should be able to build up the value of the distribution of the V, and then you simply connect the point, and then you come up with the curve. This is called the V versus X, the shear diagram. Okay, in principle is in this way, and the same repeated, the sweeping the selected cross section throughout the whole beam, and you should be able to discover to find out the bending diagram. Okay, so that is the principle here. And you may ask me, by keeping sweeping the selection of the cross section, would that be very tedious? Yes, the answer is yes. So there are some kind of the effective and efficient techniques, and that allow us to do the work very smartly, and that will be talked about in the next section here. But this is a principle, okay? And right now, before we move on, and here basically here we let me introduce new terminologies. So if you choose the free body diagram of this portion, then that is the cross section you exposed to find out the direction. And this cross section, you can see it out normal direction is kind of face right. So that is the out normal. Sorry. Okay, so that is the cross section that exposed to the face right, and these sections and that has an out normal face left. Okay, so basically here I use face right or face left to indicate that the section, this cross section, because the either a cross section face right or cross section face left, that will matters about the signs and we use to describe the shear and moment individual section here. So here it's time for us to find out to define the sign convention. So for a cross section that is face right, then here and for cross section that face left, and that is the sign, positive sign for shear. And for face right, we define the positive shear is downward. For face left, we define the positive shear point upward. And no reason to explain and no explanation why is this, because this is a convention. Convention, that means people define it, we take it. Okay, so in this portion you simply memorize, no reason to explain. Okay, just memorize the sign convention. And so here we can exercise, and with this one we can try to draw the shear diagram here. So say we repeat our exercise. So let me say pick a cross section here, okay, and then here let me pick this portion of the free body diagram. And so basically this one is a section and face right. Okay, so let me note that one. Okay, so and then here we put onto this is the force here and P over 2. Okay, so this free body diagram didn't include P here, so here we can proceed by doing the equilibrium. So from here, very simple, by doing the equilibrium you should be able to find P over 2 here. Okay, and that's a V. So that is the direction obtained by equilibrium in this one. Then we check this one against the sign here. So right now we can see this is the magnitude of P, and by equilibrium that is downward. Now we accommodate to the sign convention here. This one basically deemed as a positive. So here, so for these sections corresponding to here, the value equal to P positive. Okay, again we use, let me repeat one more time. The first, we apply the equilibrium equations in vertical directions, and we obtain that force must be equal to P over 2 and downward to imbalance it, to be imbalanced with this one. And then this is a shear force, so I use V here to indicate this is a shear force. And now the next step is to, based upon the calculated result, to check with the sign convention. And for sign convention, for this case, downward as positive, so that means here I put this point as a positive in my shear diagram here. And from here you can see, if you keep changing the sections, as long as it remaining between AC, you can see that one reaction should be constant throughout the selection in this segment here. Okay, and now let's move to the other options and the other segment. So say for between C and B, let me pick this section, and for to ease the calculation, so let me pick these portions as my free body diagram, because that involves less number of the loading. And here this is the P over 2 is given here. Okay, so again here we using the equilibrium equations, then we know that should be P over 2 and downward to be in balance with this one. Okay, and now the next step we calculate the direction against our sign convention. So for this case, this is the face left section, so we use this one. For face left action, the action here, the positive is upward, and now based upon we calculated, our calculator is here, and by inserting the definition sign convention here we can see the value should be negative. Okay, so the value, let me put into color here. So that should be negative. Okay, so this one is negative P over 2 minus, and again for this case you can see if you keep changing your sections as long as maintaining in portion BC, that is constant P over 2 here. So by doing so, this constitute the shear diagram for this example here. Okay, so that is one here. And then for bending moment, for the face right and face left sections, and we defined a positive as like this. Okay, again you need to memorize the sign conventions, and for this case, and here is an easy way, a hint for me to memorize is this: the positive bending basically will curve up the beam. Okay, so that's the way I memorize these things. So here we can exercise the same example here. Okay, so here you can see I pick the same sections, and for that section I pick this free body diagram. So that is a free body diagram I pick. Okay, and that's a given P here, and this portion V equal to P over 2, that's what we previously calculated. So based upon this one, so how about this? Let me repeat this one here. So that is the free body diagram, and this is the P over 2, and this is P over 2 we've been previously calculated in the previous slides here. Okay, so now for this case we take the bending, for example, about the point A and equal to 0, and my goal is to determine and what is the direction here. Okay, so I want to determine M. So by doing so, you can see basically M plus P over 2 times, for example, the distance here is X, okay? And here they basically opposite direction, so this should be negative, okay, equal to 0. So M equal to P over 2 times X, okay? So here this is P over 2x, and then again based upon our sign conventions, and you can see the sign convention is this. So let me do this again. This is the face right, and this is positive sign for bending. Okay, so right now this one, our this is P over 2 times x. Our calculated result P over 2x is in this direction. That is based upon equilibrium. Right now we check against the sign convention, and we found this is positive to be drawn on the bending diagram. So that is, here is x, and here P over 2x here. Okay, so basically here you can see this bending really doesn't matter if we keep changing the sections. They have always have this pattern here. So the pattern basically is a straight line and with a slope and P over 2 here. Okay, and now we can keep working on the other side. And so say for this one I pick these sections, and then the free body diagram is simply like this here. Okay, and this is a section we come up with, and then again this is the previous calculated directions there, and that is the force given here. So by doing so, you can see the bending equal to this. Okay, so let me recite this again. For this face left cross section, we have the bending equal to P over 2 times X. And what is X? X I measure from here, okay? So in this case, again, our face left and positive bending is defined in this way. So here for this case, we know when we draw, this can be drawn as a positive number in the bending diagram. So that is the positive. We know that point should be in the upper portion here, okay? And now X is measured from here and with a slope P over 2. So basically under these things, the curve will be something like this and P over 2 here. You see when I draw the curve, I start from here and moving leftward to accommodate the coordinate I pick up here. So that is the bending curve, and so constitute the two portions together. That is the bending diagram for this example here, okay? So basically here we pick up the two sections individually and to come up with this one. So one more time, and here is a summary of the sign conventions, and this is our textbook and one way to memorize, and this is my notation. Positive sign for face right, and that is this, and for face right, face left is this, okay? And no explanations about why is this, because that is a conventions. People define it, you simply memorize, okay? You need to memorize this one here, okay? You need to memorize the sign conventions, for otherwise we wouldn't be able to talk about these things on the same the baseline. You need to memorize this sign here. So that is the most important piece and for you to take home at the end of this section.